Good evening, Lamai. Today we are going to discuss about the directing nature or the directing abilities of substituent groups of benzene ring, basically monosubstituent benzenes. That is what is there in our syllabus, right? So let's discuss about the directing ability of substituent groups of benzene ring, basically monosubstituted benzenes, right? The idea is this, Lamai. So basically, right, if you think of a monosubstituted benzene ring like this, right? Monosubstituted benzene ring. That means you have a substituent group connected to the ring. Let's take like this. A substituent group is there, right? If you think of this kind of monosubstituted benzene ring, this referred to as monosubstituted benzenes. One substituent group is there, right? So for these benzene rings, the positions which are adjacent to the carbon which is there in the substituent group are known as the ortho positions. Ortho positions, right? The positions of the benzene ring which are actually adjacent to the carbon we are in the substituent group are known as ortho positions, right? Then the position directly opposite to the carbon we are in the substituent group is referred to as the para position, right? The para position, right? And the position of carbon between the ortho and para positions is actually known as the meta position, right? So this is meta, as well as this position is also known as meta. Like this, right? The 5 other carbons or the positions of 5 other carbons other than the carbon we are in the substituent group are known as ortho, para and meta positions, right? According to these positions, right, the second group will be substituted to this benzene ring, right? Okay, let's just go to the note what they are saying, right? So at the page number 20, right, they are saying when a monosubstituted benzene undergoes a heterolytic substitution reaction, the place where the second substituent group attached will be determined by the nature of the first substituent group, and the relative positions of monosubstituted benzene ring are referred to as, right, the positions of carbons which are adjacent to the carbon which carry in the substituent group is called as the ortho positions, and the position of carbon which is directly in front of the carbon which carries the substituent group is the para position, and the two positions which are in between the ortho and para, two positions which are in between the ortho and para are known as meta positions, right? So that is how the monosubstituted benzenes are labeled. The positions of the monosubstituted benzenes are labeled, right? So these are the ortho positions. This is para and meta. Let's discuss about some examples. See, you should think of these examples, right? If you think of this is a monosubstituted benzene, right? So that these two positions are known as ortho positions. The adjacent carbons to the carbon we are in the substituent group are known as ortho positions, right? The position directly at the opposite of the carbon we are in the substituent group is referred to as the para. This is the para position there. And the positions between the ortho and para are known as meta. These are the two meta positions, right? Got the idea? So some other example. So if you think of another ring, benzene ring, right? Like this. See, some VR is connected. So two positions adjacent to the carbon we are in the substituent group, these two positions are known as the ortho positions, right? So the position directly opposite to the carbon we are in the substituent group is referred to as the para position, and the two positions in between the ortho and para are referred to as meta positions. Right? So the idea is clear. That is how the positions of the monosubstituent benzenes are labeled. Right? Okay? Clear? Done. Right. Let's discuss about how the second substituent groups or the second substituent groups or the electrophiles will be directed to this ring. Let's discuss about that thing. Right? If you need to come up with some benzene ring with two substituent groups, right? You need to direct another new electrophile to this one, right? To come up as the second substituent group, right? Let's discuss about to which positions the electrophiles will be directed in monosubstituent benzenes, right? Okay. When it comes to these substituent groups, the first substituent group, when it comes to the first substituent group, I refer it as A, right? There are two kinds of first substituent groups, right? There are two kinds of these first substituent groups, right? One are known as ortho-para directors, the others are known as meta directors. Let's discuss, right, what this means, right? So, first let's discuss about the ortho-para directors. Ortho-para directors. Ortho-para directors. Ortho-para directors, right? Or ortho-para directing groups. Ortho-para directing groups. The idea is this one. So, if you are trying to connect a new electrophile to a monosubstituted benzene, if you are trying to connect a new, if you are trying to connect a electrophile to a monosubstituted benzene, right? Those will be directed, right, to ortho and para positions if the first substituent group is known as an ortho-para director, right? Let's see what that says, right? So, if you have a benzene ring, right, which is with a ortho-para director, let's say this first substituent group is a ortho-para director. If this one is kind of ortho-para director, then the second substituents or the new electrophile will be connected to the ortho-O para positions, right? So if you are trying to, let's say, if you are trying to come up with, right, this kind of a thing, conc HNO3 conc H2SO4, this is used to add NO2 group, no? This is used to supply the NO2 plus electrophile to the ring, no? Right? So, if you are with a ortho-para director at the ring, then this new electrophile, the new electrophile will be substituted to the ortho position or to the para position. Ortho position or to the para position. Right? This is the ortho position and this is the para position. Right? That is the idea, right? So if you are with the ortho-para director at your ring, when the second electrophile, the new electrophile is to be added, right? Then the new electrophile will be directed to the ortho position or to the para position. Right? That is what the ortho-para directors do. Right? So as these ortho-para directors, we can identify these stuff, right? So if this A group, right, is kind of a NO2 group, sorry, if it is kind of a OH group, right, or NH2 group, or it could be a OR kind of a group, or it could be just the R group, alkyl group, right? All of these are referred to as orthoparadiators. Not only those, right? It could be a NHR, or even the halogens, Cl, Br, those halogens. All of these are referred to as orthoparadiators, right? All of these are referred to as orthoparadiators. Right? So this is the idea. Okay, let's think of some examples here. See, some examples. Let's say you are with this monosubstituted benzene, some R group is there, and let's say you are adding some electrophile. Let's say you are coming up with this one, with anhydrous AlCl3. So as this one is orthoparadiator, right, this new electrophile, what is the electrophile you are supposed to add from here, right? This is the electrophile now. This is the electrophile you are providing with this reagent now. It will release this thing, and this thing will be connected now. So that thing will be connected to ortho and para positions, to the ortho position as well as to the para position. That is what the orthoparadiators does. To the ortho position and to the para position, the new coming electrophiles will be connected if you are with the orthoparadiator at your ring, right? So the idea is clear. So let's discuss about another example. Say you are with this one, let's say you are with some Cl here. So this is referred to as orthoparadiator. See, orthoparadiator. So that, right, if you add this kind of stuff, CH3 Cl with anhydrous AlCl3, right, what will happen? This electrophile, this new electrophile, the new coming group, will be added to the ortho and para positions of this ring, right? Ortho and para positions of this ring. So you have the Cl here. So where's the ortho position? The ortho position is one out of these two, right? I'll add the new thing to here, the ortho position, right? This is the ortho connectivity. The new electrophile, this thing will be added to ortho position or to the para position. To the para position, right? This is the para, directly opposite, right? This is what the orthoparadiators does. the new coming electrophile, this thing will be added to the O2O para positions of the benzene ring, right? So that these are referred to as O2 para reactors, O2 para reactors, right? Okay, got the idea? Right. Let's discuss about the other kind, right? Let's discuss about the other kind of reacting groups, right? The second type of reacting groups are referred to as meta-reactors, right? Meta-reacting groups, right? Meta-reacting groups. Meta-reacting groups. Say you are with this kind of a monosubstituted benzene, and say this one is kind of a meta-reactor. Then what happens? Then if you're trying to add some new electrophile, to the ring, right? Then that electrophile will be directed to the meta position of the ring. Right? So what is the meta position? So these two are O2 positions. This is the para position. So in between the O2 and para, you see the meta position. So the new electrophile, the NO2 plus, this reagent is added to provide the NO2 plus electrophile that will be connected to the meta position of the ring, right? Meta position of the ring. If you are with a meta reactor at your ring when the electrophile arrives, right? So what are these meta reactors? Let's discuss about those things. Meta reactors are these ones, right? Here, if these groups are connected to the ring NO2, right? Like this kind of a group, like Couch group, carboxylic thing, right? Or kind of aldehyde group, ketone group, or it could be cyanide group. If these groups are connected to the ring, these are referred to as meta-reactors. So the new electrophile will be directed to the meta position of the ring, right? Okay. So even this one is kind of a meta-reactor, right? Let's see some examples. Right? See, you are with a meta-reactor, right? This is a meta-reactor, right? So if you are trying to add some new electrophile, let's say you are trying to add some Br plus electrophile by adding this reagent with this catalyst, right? So you are supposed to come up with a Br plus electrophile. So what will happen? The new electrophile will be added to the meta position of the ring. So these are the O2 positions, this is the para position, and this is the meta position, right? No? So new electrophile will be added to the meta position of the ring. That is what the meta-reactors do. This is a meta-reactor, so new electrophile will be added to the meta position of the ring. right? Okay, let's come up with another example. See, you are the NO2 group, which is also a meta-reactor, right? Okay, let's try to come up with what kind of stuff, right? Let's try to add some this kind of group. So this reagent is added to supply this electrophile, right? So that is a new electrophile which is supposed to add to the ring. So that will be directed to the meta position of the ring. Meta position of the ring. So you have the NO2 here. So these are the ortho positions. These are the ortho positions. This is the para position, directly opposite. And between the ortho and para, you have the meta. Here and here, the meta positions, right? So to the meta position, the newcomer will be connected, right? That is the new coming group, no? That will be connected to the meta position. See, to related to this position, this is meta position, right? Okay, so that is what meta reactors do, right? That is what meta reactors do. Idea is clear, right? Okay, let's discuss why some of these first substituents behave as orthopara reactors and why the others behaves as meta reactors. Let's discuss the reasoning, right, of these reacting abilities of these first substituent groups, right? Okay, first discuss about the orthopara reactors. Orthopara reactors. Right. Reasons behind the directing abilities of first substituent groups. Right? This is about the reasons. Right? First, about the orthopara reactors. Right? First, about the orthopara reactors. Right? Right. The idea is this, Lama. Let's take this example. Right? Let's take this example. Right? This is one reasoning for the directing ability towards the ortho and para positions. Right? Let's take one of the orthopara reactors. Example, phenol. Phenol is considered as an orthopara reactor. Right? Okay, this is the phenol. Orthopara reactor phenol, right? Right, phenol. Right. This is what happens. So basically, this lone pair on phenol will be directed to the ring like this. Will be to the ring like this, right? So this lone pair comes towards here, so that this bond leads to here, because only 4 bonds can be there with the carbon. So with that, you will come up with this kind of a structure. There's a minus here, right? This is the situation, right? So you will come up with a positive here. Then what will happen? This pair will be donated to here, while this comes here. So that there will be a minus charge on this carbon. I'll just write it like this, no worries, no? So then this pair, this electron pair will come towards here, and so these electrons will be left here. So you'll come up with this resonance structure. Right? Ultimately, this could come towards here by this removes to this one to come up with the final resonance structure available. Right? This is the resonance hybrid of phenol. This is the resonance hybrid of phenol. This is referred to as a resonance hybrid of phenol, right? So when considering this resonance hybrid of phenol, you could clearly see some minus charges are appearing. That means electron rich areas are appearing with the O2 and para positions of the ring. So here this is the O2 position. At the O2 position of the ring, minus charge is appearing. Right? At the para position of the ring, directly opposite position, para position of the ring, minus charge appearing. At the O2 position of the ring, minus charge appearing. Right? So the new electrophile, the electron loving group, if you have with a new electrophile, right? That means electron loving group that will be surely attracted to the relatively electron rich areas of the ring, right? As the electrophiles are very keen to get attracted to the places where you have more electron density, as those are electrophiles, electron loving groups. This new electrophile will greatly attract towards the positions where you are with much more electron density. So those are the positions, actually the O2 and para positions of the ring. Those are the O2 and para positions of the ring, towards here as well as here. The electrophiles will attract. This electrophile will attack towards here as well, no? So electrophile is keen to get attracted to the O2 and para positions of the ring. So that is why these guys are referred to as O2 para directors. That is why the phenol is referred to as an O2 para director. So basically O2 para directors direct the new electrophile to the O2 and para positions of the ring. Right? That is why those are referred to as O2 para directors. So that will be done by this kind of a resonance hybrid. in some instances. With the phenol as well as with the aniline, this kind of resonance hybrid is available, where the ortho and para positions are with negative charges with some great electron densities, so that the electron loving groups will attract towards those positions of electron rich areas, right? So the ortho and para positions will be attacked by the electrophiles then, so that those groups are referred to as orthopara detectors. The phenol is kind of orthopara detector then, as it will activate the ortho and para positions of the ring, right? So phenol will activate, right? Because this thing we can say is resonance hybrid. Actually, phenol has activated the ortho and para positions of the ring. Right? With resonance hybrid, phenol has activated the ortho and para positions of the ring. So electrophiles will attract or attack to ortho or para positions. Actually, not ortho and para positions of the ring, right? The idea is clear. That is why these are referred to as orthopara detectors. Phenol is one such example, right? Okay, the idea is clear, no? Right. This is about the second reason. Right? Why these how these orthopara detectors are able to detect the new coming electrophile towards the ortho and para positions, right? This is about the second reason. There are two reasons, right? One is due to the resonance hybrid, the nature of the resonance hybrid, right? Let's discuss how the ortho and towards ortho and para positions the electrophiles are detected by something like a methyl group, right? See, this can be that example as well. Another example, toluene. Let's take this example, toluene. Right? If you think of toluene, its resonance hybrid, it looks like this. It is referred to like this, right? Toluene. Right? Let's think some electrophile is connected to this one. This is the second reasoning, right? This is reason number 2. Why these guys are referred to as orthopara detectors, right? Right. If you think of the stabilization of the uranium ion, when the new electrophile is connected to the ortho and para positions, let's connect this thing to the ortho position. When the new electrophile is connected to the ortho position, right? See, let's discuss some new electrophile, right? When the new electrophile is connected to the ortho position, right? So what will happen? So this bond will break like this, and you get a positive charge here. right? So if you think of the resonance structures here, these electrons comes to here, right? Giving a positive charge to here, right? This is all about the stability of resonance hybrid, right? Stability of the uranium ion. So to utilize this thing, these guys will come here. So the positive charge will come to this position, right? So this is the resonance hybrid of uranium ion formed. So you clearly see this resonance structure can be stabilized by the electron donating edge of CH3. This resonance structure can be stabilized, right? Can be stabilized by electron donation, right? So one of the resonance structures of the resonance hybrid can be stabilized by the electron donation, right? So that resonance hybrid gets some greater stability, right? If the electrophile is connected to O2 position, right? This is all about stability of uranium ion, right? Let's discuss what happens when the newcomer connected to the para position. Still you would see the same kind of a structure, right? Same kind of a thing. If the thing is connected to the para position, the new electrophile, right? So you could have a positive charge here, no? If the things are like this, the uranium ion. So you can utilize this positive charge by giving some electron pair to here, so that positive charge come to here, CH3, no? So neutralize this one, you could do the positive charge, you could release the electron pairs to there, right? So you clearly see these are the three resonance structures available with the uranium ion, right? So this thing also can be stabilized. So this resonance structure can be stabilized by electron donation. So to this kind of a orthopara detector, if the newcomer is connected to the para position, still one of the resonance structures can be stabilized, so that the resonance hybrid will get some extra stability, right? If the newcomer is connected to the O to O para positions, this is the ortho connection, this is the para connection, right? Such stability won't appear if the newcomer is connected to the meta position, right? You could see that, right? If that newcomer is connected to the meta position, such stabilization won't occur, right? So as the orthoparaditors are able to stabilize the resonance hybrid of the uranium ion, right? The newcomer electrophiles will be directed to the ortho and para positions, right? But if the newcomer was connected to the meta position, such stabilization won't occur. You can do that thing and see whether such kind of thing is available. If the newcomer is connected to the meta position, that won't occur, right? This is the second reasoning, right? So the two reasons have been given, right? Why the orthoparaditors direct this newcomer electrophile to the ortho and para positions. The two reasons are, the one thing, the first thing is actually the orthoparaditors will increase the electron densities of ortho and para positions of the ring, so that electrophiles will direct to that thing. That is one reason. The second reason is actually the stabilization of the uranium ion. When the new electrophile is connected to the ortho and para positions, right? If you are with the orthoparadiator, those guys can stabilize the benzene ring, right? So get some extra stability, right? So such kind of connection is possible, right? No, those are the two reasons, right? This is about the meta thing as well. By the meta reactors direct the second electrophile to the meta position. This is about that thing as well. Right, this is about the meta reactors. Right, meta reactors. The thing is Islamite, right? Let's get some come up with some example. As an example, let's take the nitrobenzene, right? Let's take the nitrobenzene, right? So this is nitrobenzene, right? So what beta reactors do? Basically, as these electrons are more attracted towards the oxygen, this bond will break like this, so that as nitrogen is lack of 4 bonds, right, this pair will come towards here. As nitrogen is lack of 4 pairs, right? Octet is not there, no? So you will come up with a structure like this. Right? Then you get a positive charge at this position. Right? So ortho position is positively charged. Then to neutralize that positive charge at the ortho position, this pair comes towards that. Then what will happen? Then the charge is delocalizing towards the para position. Right? So neutralize the charge of the para position as these electrons are coming towards here. So you would observe again some charge appearing on the ortho position. So with this resonance hybrid, right, you would clearly see positive charges are appearing on O to N para positions. So that means O to N para positions are deactivated towards electron loving groups. Here, the O to N para positions are deactivated. So positive charge means those positions are deactivated towards electron loving groups, which are the electrophiles. So electron loving groups won't attract towards here, towards the O to N para positions. So that the electrophiles will attract towards towards the meta positions. So positive guys won't attract towards the positive positions, right? So these are the electrophiles now. So that electrophiles will attract towards meta positions. Towards meta positions, electrophiles won't attract towards the O to N para. So that means those will prefer the meta positions, right? So O to N para positions are deactivated towards electron loving groups. So electrophiles will be directed or attracted towards meta positions, right? Towards meta positions. As O to N para positions are positively charged, electrophiles won't come towards the O to N para positions. So it will attract towards the meta positions. So what they are doing is actually O to N para positions are deactivated. This is what meta detectors do. Meta detectors are not going to activate the O to N meta position. Meta detectors are not activating the meta position, but the meta detectors are deactivating the O to N para positions. That is why the electrophiles will be attracted to the meta positions. Right? Got the idea? So the summary is actually, right, orthopara detectors activate the O to N para positions so that new coming electrophiles will attract towards the O to N para positions. Right? This is what orthopara detectors do. When it comes to meta detectors deactivate the O to N para positions so that new coming electrophiles will be attracted to the meta positions. So orthopara detectors, meta detectors, all the things do the action to the O to N para positions. Orthopara detectors activated the O to N para positions, meta detectors deactivate the O to N para positions. Right? So the electrophiles will then attract to the relatively electron dense areas. Right? That is the idea, right? Okay, so that is how the meta detectors direct the new coming electrophile towards the meta positions. Right now, the idea is clear, right? Okay, so normally lamai meta detectors, all the meta detectors are known as deactivators. All the meta detectors are known as deactivators. Those will deactivate the ring, or those will decrease the electron density of the ring, right? So with these things you can clearly see the ring is positively charged. All the meta detectors are so known as groups which deactivates the ring, or electron withdrawers, right? So all the meta detectors are known as electron withdrawing groups. These are electron withdrawing groups, right? other than the halogens, all the orthoparadiators are electron donating groups. You had seen about the CH3 situation, you had seen about the OH situation, the same with the NH2, right? So other than the halogens, all the other, right, all the other orthoparadiators are electron donating groups, right? Halogens and all the metadiators are electron withdrawing groups. Keep that in mind as well, right? Okay. So summary, I'll give you a summary, right? So this is the summary. Right? First, the ortho para directing groups and the meta directing groups. Right? The action is actually, if you are with the orthoparadiating group, right, the new electrophile will be added to O to O para position, no? Those are the orthoparadiators, no? Right? So, what those groups? Those are OH groups, OR groups, NH groups, NHR groups, any alkyl group, and halogens. Right? And metadiators means those are the groups we direct the new coming electrophile to the meta position. Right? So, what are those groups? NO2 group, OH group, aldehyde group, ketone group, right? This one, sorry, this kind of group, right? COO, NH2, right? Or cyanide. Right now? So these are the orthoparadiators and these are the metadiators, right? All the orthoparadiators other than halogens are referred to as electron donating groups to the ring, right? And these guys and halogens are referred to as electron withdrawing groups from the ring. Right? This is the simple summary. Right? All the orthoparadiators other than chlorine are referred to as electron other than halogens, right? Chlorine and halogens are electron donating substance groups, and these are electron withdrawing substance groups. That is also should be known, right? This is about the E, right? The first substance, right? Okay. So if you need to identify by just merely looking at the group, if you need to identify whether it's a orthoparadiator or a metadiator, what you should do is this, Lamai. So basically you can clearly see some important structural nature of all the metadirectors. It comes to all the metadirectors. All metadirectors carry this special structural nature. See, the special structure is carried by all the metadirectors. By looking at this, you can identify whether a metadirector or a orthoparadiator. No need to memorizing the stuff, right? So when it comes to metadirectors, right, that connected atom to the benzene ring is always with a 5 bond and electronegative atom connected to that thing, right? Always the connected atom to the benzene ring is with a 5 bond and electronegative atom. 5 bond and electronegative atom. This guy is with a 5 bond and electronegative atom. This guy is with a 5 bond and electronegative atom. Here 5 bond and electronegative atom. With the atom connected to the ring. Here 5 bond and an electronegative atom. So if your group contains a 5 bond and electronegative atom, if your atom which is connected to the benzene ring is with a 5 bond and electronegative atom, so those are referred to as metadirectors. If that requirement is not met, right, those are orthoparadiators. It is how we prefer you to remember these things. No need of memorizing, right? You can do that check. If the atom connected to the benzene ring is with a 5 bond and negative atom connected to that thing, right? So those are metadirectors. The others are orthoparadiators. You won't see 5 bonds appearing here, right? No? The idea is clear. No? That is how we are supposed to identify the orthoparadiators and the metadirectors. Clear? No? Right. Let's move to the next section. Right? Let's move to the next section. Right, when we have to think of this second group attachment towards the monosubstitute benzene rings, right? Okay, we could see some special reactions. We could see some special reactions appearing. Let's discuss those things, which is there at the page 22, right? So some special note here. Some special note here. These are some special reactions, right? Some special one, right? You need to concern when doing the conversions, right? The first thing is this, right? The Fiedel-Crafts. The Fiedel-Crafts alkylation is not possible. The Fiedel-Crafts alkylation is not possible when a substituent group which is more deactivating than halogen, is more deactivating than halogen, is connected to the benzene ring. See what this is? It says the Fieldcraft alkylation is not possible when a substituent group which is more deactivating than halogen is connected to the benzene ring. So a substituent group which is more deactivating than halogen means, this means this is all about meta-directors. This is all about meta-directors. Meta-directors are deactivating guys. Meta-directors basically deactivates the ring, right? So this is all about meta-directors, right? So simply this says when you have meta-director, you can't do the alkylation. That is the idea. So if you are with this thing, right, and if you are adding this one, thinking of alkylation, actually that won't happen. No reaction. Alkylation is not possible, right? Alkylation is not possible. Alkylation is not possible when you have a substituent group which is more deactivating than the halogen is there with the benzene ring. So we are thinking of adding this alkyl group here, right? But that won't occur. These are some special reactions you should avoid. These are some special situations you should avoid when doing a conversion, right? You have to avoid these things, right? So you won't see the production of some CH2 group here. That won't happen, right? Okay, no reaction possible here. The next one, the second thing to note that these are special situations you should avoid when doing conversions, right? Number 2, right? Fieldcraft reactions are not possible with phenol and aniline. Not possible with phenol and aniline. Right? So if you think of phenol, this is phenol now. Right? You would think if you add CH3, CH2Cl with anhydrous AlCl3, or if you add CH3COCl with anhydrous AlCl3, that is how the Fieldcraft alkylation and acylation is to be done. You may think of that as phenol is orthopara director, you may think that this should occur at the ortho position and the para position. But keep that in mind, these won't produce, right? For Fieldcraft reactions are not possible with phenols and aniline. This is your expectation, but that is not happening. These are not possible. These won't happen. No reaction. No Fieldcraft alkylation, no acylation with phenol as well as aniline. Right? With aniline also, this won't occur. right? Fieldcraft reactions are not happening. The reason for this is actually, right, the lone pair on phenol as well as aniline will be donated to the Fieldcraft catalyst. At AlCl3. And so catalyst will consume. So there is no catalyst to do the reaction, right? So deactivating the catalyst is the problem. Deactivating the catalyst in simple terms, so that Fieldcraft reactions won't occur with aniline and phenol. Remember that, right? That is very important stuff to remember. Okay. Next one. These are some special situations appearing with the monosubstituted benzenes when you are trying to connect the second group to the ring, right? Number 3. Number 3. Number 3 is about nitration. Nitration can't be done as expected with aniline, right? So normally one may expect, if you have to add some conc HNO3 with conc H2SO4, one may expect to produce some more of O to N para products, as NH2 is kind of a O to para reactor. Right, this is expectation, right? But actually with aniline, you won't see a considerable amount of this thing, right? But reality, the reality is with this reagent, you won't produce that much of O2 product. The reality is this thing and para product. So we are expecting O2 and para to produce, but what produces is para and meta, right? Actually O2 is not happening, right? So 51% of para product and 47% of meta. So that is not as expected, right? We have a problem with the auto product. So reasoning is mentioned with your dude, right? Go to that. So you can't obtain the auto product as expected, right? This is the reality. The reason for this is actually this guy tends to behave as a meta director. This guy is tend to behave as a meta director, as the lone pair on this thing is right given to here. It's acid-base reaction and kind of meta nature comes to the ring. As this becomes NH3 plus, is this nitrogen getting some plus charge, it tends to attract electrons much from the benzene ring and giving some meta characteristic to the ring, meta directing nature to the ring, right? So that is why some possibility of meta things are also there, right? So you won't get the auto product as expected by just adding the conc nitric, conc sulfuric with the normal procedure with the aniline, right? So that is a special thing. So just go to the note at the page number 23. You can clearly see the explanation, right? Not that much. They won't that much ask the reasons why is that, right? But avoid this reaction. Don't put the normal nitration mixture to come up with the auto product when you have aniline. So because of this acid-base reaction, some considered meta product will be also produced, right? Okay. The next special reaction with the monosubstituted things. These reactions are special stuff, Lama. Right? Not happening normally. These are abnormal situations with monosubstituted benzene rings, right? Number 4. Right? Number 4. This is about esterification. Using phenol. Phenol is also a monosubstituted benzene ring, right? So, with the use of alcohol, right? You can use carboxylic acids as well as acid chlorides, both the stuff, to come up as phenols. Alcohols with carboxylic acid, in the presence of H2SO4 catalyst, you get the esters. Alcohols with acid chlorides, you get the esters. But when you are with phenol, right, only the acid chlorides are able to produce the esters, not the carboxylic acids. That is also a special thing, right? So when it comes to phenols, right? Sorry, I like this, right? So when it comes to phenols, the carboxylic acids, right, can't be used to produce the esters. So this pathway with conc sulfuric and heating is not available to produce the esters. When you are with phenol. Normally with aliphatic alcohols, you are able to produce phenols like this. Carboxylic acid pathway is not available when you are with phenol. To produce the esters, you definitely need the acid chlorides. When phenols are there, right? Now you can come up with the ester. Right. So esterification can be done only with use of acid chlorides, not with carboxylates. Right. The reason for this thing is actually phenols are considered as very weak nucleophiles. These are considered as very weak nucleophiles. Not like in alcohols, these are very weak nucleophiles now. Right? These are very weak nucleophiles. Your electron pair on oxygen is delocalized through the ring. Through the ring, the electron pairs are delocalized. So these are referred to as weak nucleophiles. So with this kind of weak nucleophile, you can't attack the carboxy acids, right? So as these are considered as very weak nucleophiles, phenols are very weak nucleophile, right? Here also weak nucleophile. You can't attack the carboxy acids. Right? But as in acid chlorides, the chlorides are behaving as kind of very good leaving groups. As chlorides are behaving as kind of good leaving groups, then even with a weak nucleophile, the attack is possible. Right? As chlorides are referred to as very weak, very good leaving group. Right? That is the idea. So the point is, phenol is considered as a weak nucleophile. Right? So attack towards carboxy acids are not possible. Right? Are not possible. With acid chlorides, you have a good leaving group, so that this porosity is much greater, this carbon, than the porosity here. Right? So that this is possible. Right? The problem with this not reacting with carboxy acid is the phenol is considered as a weak nucleophile. So attack towards the carboxy acids are not possible. Right now? The idea is clear, no? Right. That is the fourth special kind of reaction with monosubstitute benzenes. Fifth kind. The fifth special reaction kind you should know before going towards the conversions of these benzene things. Fifth case. Phenols and anilines are considered as highly activated benzene rings. We had discussed this thing last day, right? When we are when we are starting the conversions related to benzene, right? Phenol and anilines are considered as highly activated benzene rings. So special reactions are happening, right? So that these special reactions will occur with the phenols and anilines, right? The first thing is about bromination or halogenation, right? When it comes to bromination or halogenation, right? If you are adding the Br2 or Cl2, right, to benzene, you won't see a reaction happening. If you are adding Br2 or Cl2 to benzene, no reaction would occur, right? But if you are adding, if you have to add the same Br2 to phenol or to aniline, see what will happen. You can use the Cl2 as well, right, with the phenol and aniline. What will happen? You would observe these tribrom products which appears as white PPT. Those will form, right? These tribrom products will form. So this is possible as you are with highly active benzene rings, right? 246 is 246 tribromo phenol. It's a white PPT. This is also a 246 tribromo aniline. This is also a white PPT. Right? These two results are possible with just adding Br2, as phenol and aniline rings are highly active benzene rings, right? So that is not possible with particularly benzene. To add Br2 to benzene, you need a catalyst. Without the catalyst, the reaction won't occur. This kind of special situation appearing with the bromination, as the phenol and aniline are highly activated rings, right? Okay, let's discuss about the second special kind of reactions with the phenol and aniline, right? That is about nitration. It is about the nitration. It's about that thing as well. B is about, right, nitration. B, nitration, right? So to add the NO2 group to benzene, you need consider HNO3, consider H2SO catalyst as well, and some 50 degrees temperature as well to add a NO2 group to benzene. The requirement towards benzene. But when it comes to phenol, right, adding the same reagent actually will give you trinitro product, like in BR2 situation. Trinitro product. See? Right? 2,4,6 trinitrophenol. This is also known as picric acid, which is a very strong acid, right? So that in the same region to phenol will give you the trinitro product, not the monosubstituted, not the single substituted NO2, right? So if you need to come up with orthonitrophenol or paranitrophenol, what you need to do is you need to add just the dill HNO3, just the dill HNO3 at 20 Celsius. No need of heating, temperature should be 20 Celsius. If you add dill HNO3 with that temperature, you can obtain the ortho product and the para product. So if you are thinking of connecting only one NO2 group to the ring, you need to add the reagent at 20 Celsius, but the dill form, right? So ortho and para mixture will formed only if you have added dill HNO3, not the conc, dill HNO3 without the catalyst at 20 Celsius, right? So that is a special thing happening in the phenol because of its highly activated nature, right? So it's referred to as a highly activated. Right now, okay, that is all you should know about special reactions appearing in the benzene ring, right? So let's discuss about the conversion part related to this, right? The conversions, compound synthesis process. Let's discuss about that thing. Let's discuss about how to do this kind of a conversion, right? Okay, how to think, right? Here the first conversion is about starting from benzene, you need to produce this compound, right? So basically first thing to examine is actually the relative positions of these two guys. Basically, we clearly see this NO2 is connected meta to CH3. The NO2 is connected meta to CH3. The CH3 is connected meta to NO2. So basically we can say the two groups are connected meta to each other. Right? Two groups are connected meta to each other. Right? This means what? Two groups are connected meta to each other means when the second group is coming towards the ring, right? There should be a meta direct at the ring. Then only the second group will be connected to the meta position of the ring, right? So again I'm telling you, and we can say, right, the two groups are connected meta to each other. That means when second groups came to the ring, there should be, that means when second group came to the ring, there should be a meta director at the ring. That is the idea, right? The two groups are meta to each other means, right? When the second group is approaching the ring, there should be a meta director at the ring. So first you have to connect the meta director. So first connect the meta director and then direct the second group to the meta position, right? So that is how we are thinking here. So here, this guy is a orthopara director, this guy is a meta director. This guy is orthopara director, this is a meta director. So we need to connect this one first. We need to connect this one first, right? Okay, no? We need to connect this one first. First connect this one, then secondly connect this one, right? Okay, no? So that is the first thing, right? So let's take this one as okay. Let's connect this one and then you can connect this one, right? Let's do the stuff, right? So this is how we are supposed to connect the things. So this is your conversion. So I am completing the conversion now. Right. So first connect the meta director. First connect the meta director. You can connect this thing by using conc HNO3 and conc sulfuric at 60 Celsius. Then you can bring this group. But remember here, you can't do the alkylation. You can't do the alkylation when the NO2 is there. You can't do the alkylation. So you have to go through a acylation. Keep that in mind. Avoid those reactions which are not possible, right? Alkylation is not possible when the NO2 is there. So you have to come through a acylation, right? Acylation. Then you can convert this thing to here by Clemmensen reduction. This thing can be converted to CH2 by Clemmensen reduction, right? That is zinc amalgam conc HCl, right? Now that is how we are supposed to do this conversion, right? Actually, this is the number 2 appearing in your note, right? This is not the one number 1. This is number 2 appearing in your note. When the two things are connected meta to each other, right? How to solve this kind of stuff, right? That is number 2 in your page number 25, right? Clear now? Let's do the first example as well. And the example number 1, see what they are saying. The example number 1. So you have a CH3 group there and you have NO2 group there, no? Okay. Let's analyze the stuff. First analyze the starting and the end compounds, right? So here the two groups are connected. The two groups are connected para to each other. Two groups are connected para to each other. Para to each other, right? So that means two groups are connected para to each other, right? So that means when the second group arrives to the ring, right? When the second group arrives to the ring, there should be a para director at the ring. Only when you are with a para director at the ring, the second group will be directed to the para position, right? Okay, that's the idea. So have to connect the para director. Connect the para director first, right? So out of these two stuff, right? This is the ortho para director, this is a meta director. So you have to first connect the para director, then you can come up with this one, right? So let's solve the stuff, right? The thing is like this. So how to do? First connect the para director, CH3 group, para director. So that can be done by simple alkylation, right? Then you can connect the NO2 group by simply adding nitration reagent, conc nitric, conc sulfuric at 50 Celsius. Simple as that. Right now, this is how we are supposed to think a benzene conversion. Right? Let's discuss a bit some hard questions, half thinking patterns, right? Let's try to solve this one. Third stuff, right? What we can do here. Right. First, analyze. So the two guys are connected para to each other. Two guys are connected para to each other. Right? So we can write two groups are connected para to each other. That means there should be a para director at the ring when second group approaches. That means there should be a para director at the ring when the second group approaches. So one may think first to connect the para director. So first a para director should be connected. First the para director should be connected. But the thing here is, you see, both the guys are meta directors. NO2 group, it is a meta director, we know, as well as the Hooch group. Those are meta directors. So you don't have a para-director, right? First to connect. So what we can do? Even though we know that these two guys are not para-directors, in the process of making the COH, in the process of making the COH, you would come across a para-director. In the process of making COH, you come across a para-director, right? So you can use that thing. You can use that thing, right? In the process of making COH, you could come through a para-director, right? When that is appearing, you can bring the NO2, right? That is the idea, right? So let's solve the stuff, right? One can say it's a metadata, but in the process of making COOH, a para-director is met. See, you can do this kind of stuff, right? So you have COOH here and the NO2 appearing here. See the conversion? You don't have a para-director, but in the process of making this thing, you could come across a para-director. So we can make COH via alkylation. So which is a para-director. Alkyl group is a para-director. So as you are with a para-director, when you are with a para-director, just add the NO2 group. Just add the NO2 group. When you are with a para-director, you need to add the NO2 group. Right? By adding conc HNO3 conc sulfuric at 50 Celsius, you can do so. So now is the time to convert this stuff to COH. Convert this stuff to COH by just oxidizing the stuff. Right now? So that is how we are supposed to complete this kind of a conversion. There is a logical background to approach this kind of thing. Right? The two guys are connected para to each other means, right? When the second group approaches the ring, there had been a para-director. So first you need to connect a para-director, then you can come up with the second one. But the problem was you don't have a para-director here. So you have to think whether a para-director is available in the process of making one of these groups. Yes, that is so with the COH. So you could first come up with that para-director and then add the NO2 and convert that thing to the COH. Right? That is how we are supposed to do this thing. Right. Let's come up with the next one. Right. Let's do the example conversion number 4. Right. Okay. See, you have given this benzene, and you are supposed to come up with this one. See how to do the stuff. So these two guys are actually meta to each other. Meta to each other. Right. So you can write two substituent groups are meta to each other. That means there should be a meta director at the ring when the second group approach the ring. Now, but unfortunately, we see both are orthopara directors. Both are orthopara directors. Both are orthopara directors. We have problem now, right? The point says first you need to connect a meta director, but you don't have such, right? But you don't have such. So you have to connect a metadata first, no? That is the idea. Right? But you don't have such a metadata here. You don't have such a metadata here. But we know in the process of making this thing, you would come across a metadata, right? In the process of making NH2, right? Metadirector with NO2 is met in the process of making, right? NH2, NO2 is met. So we can use that thing, right? So let's do the conversion. This is your conversion. So first you can connect some metadirector to the ring. Right? First you can connect some metadata to the ring. Then you can introduce the second group. Always the second group should be introduced when a metadata is there at the ring. And because the two guys are with a meta connection. Right? So you can introduce this thing. But remember, when the NO2 is appearing with your ring, you can't use the alkylation. This looks like some alkyl group, but you can't do alkylation when the NO2 is appearing. So you have to go through a acylation. Can't help. You can convert the ketone thing to the alkane thing, no? You can convert the ketone section to alkane, no, by Clemmensen reduction. So don't worry to come up with the acylation in this case. Sorry, the NO2 is here, the meta section. Right? Now you can change the two guys to the respective things, right? So first you can change this one to here. By doing the Clemmensen reduction. That is zinc amalgam concrete Cl. Finally, you can convert the NO2 to NH2, NO2 NH2, NO2 to NH2 by adding tin concrete Cl and then NaOH and some heat. Right? So that is how you are supposed to complete such a conversion. Right? That is clear? Right. That is how you are supposed to think a Benzene conversion like this. Right? So you have some questions appearing in the page number 27. Right? Appearing at the page number 27. You have some questions, 12 questions there. Just try to complete those things. Right? Just try to complete those questions with the page number 12. Right? Okay. So that is all for today's lesson. Right? And do the questions and complete them and come to the class next week. Right? Let's start from here. Until the next session. Goodbye then.